remember the basic definition of a parallelogram. Two sets of opposite parallel sides. We're going to be looking at traps and kites. Anybody remember? I mean, I'm sure you've done basic trapezoid hopefully before. What's the definition of a trapezoid? It's basically based off of that one set of parallel sides. I'm showing you how this diagram is organized. A kite, no pairs of parallel sides. So this is by far the best way to organize a classification of quadrilaterals. There might be others, but this is the best one. It organizes it by number of parallel sides. All those shapes on the left that we've been dealing with have two sets of parallel sides. Trapezoid 1, kite 0. All right, so let's go back to oh, and earlier I was like, oh, I don't have a trap word cloud. I do. It was the original one. So there you go. Yeah, I found it because here was the rhombi one, and I had. Did I have a parallelogram one? You know what? Maybe I did. Now here's some vocab we might need. This is, hopefully you've done this before. Do you remember doing an area of a trapezoid? It was this. You don't have to know it. I'm just. The reason I bring that up is because there were two bases. And I'm sure you talked about the bases as being the sides that are parallel. So we just call the parallel sides the bases in a trapezoid. There's two of them. The other sides we call the legs. The other thing is we call base angles, if it's formed from a base and a leg, we call it a base angle. So there's four base angles up there. C and D are the ones that go together, and then A and B go together. Oh, also the other thing, it was on the diagram here, but I didn't really talk about it. There's isosceles trapezoids and right trapezoids. When we discuss this one, right trapezoid just means there's a right angle. And then it would have there's no other properties. It's just then there's trapezoid, basic trapezoid properties. Same with a kite. Right kite is just, there's no new properties, it's just all the properties of kite. This one has new properties though. Okay, there we go. So let's write down the definition of trapezoid. Exactly one pair of parallel sides. Now I have to throw in that this is new this year. They want us to stress definition versus properties. Definition, one set of parallel sides. Now they also want you to know that there could be a second definition of a trapezoid in which they say at least one pair of parallel sides. Don't really like that as much because then that would say a parallelogram is a type of trapezoid because a parallelogram has at least one pair of parallel sides. It actually has two. So what they're going to do is apparently if they ask you a question about trapezoids for the state test, they would then clarify exactly one or at least one. For this class, we're just going to use this, exactly one pair of parallel sides. If it was a state test question, they would have to clarify. So basic shape with drawing it would be that. Yes?
What type of trapezoid has more than one pair of parallel sides?
A rectangle.
Well, that would be a trapezoid.
Yeah.
No, they're saying a parallelogram would then be a trapezoid because it has at least one pair. It actually has two. So does that make sense? A parallelogram would then be a trapezoid. I don't like it. I don't like it. They said this is like, they want to say there's two definitions. No, there's really, the best definition is this. And this is all we're going to use. Exactly one pair of parallel sides. Because then the shape with two is a parallelogram. Two sets. Parallel sides. I know, it's kind of silly. Well, apparently, if it's a test question, they would say, all right, based on the definition of a trapezoid as exactly one pair, they have to tell you this. exactly what it is. Well, let's just go with this. And just so you know, though, they would have to clarify on a test. But we're going, in this class, exactly one. All right, now it is not a parallelogram, and it isn't, according to my definition, it's not a parallelogram, it's not a kite. None of those properties are true. There's three properties. Two of them are for an isosceles trapezoid. So first I need to tell you what an isosceles trapezoid is. Remember isosceles triangle was two congruent sides?
Yeah.
Okay? Same for an isosceles trapezoid. It's a trapezoid with two congruent legs. So two congruent sides. The congruent sides are the legs. And the other thing I need to tell you is a median. Now do you remember in a triangle there was this mid-segment? If these were midpoints, we called that a mid-segment in those properties.
Yeah.
The median is the same thing but for a trapezoid. So if that's a midpoint and this is a midpoint, we call it a median, and it will again have similar properties. So a segment that connects the midpoints of the legs of a trapezoid. It is also called a midsegment, but I use the word median to differentiate between triangle as a midsegment and trapezoid as a median. But I will say it is also at times called a midsegment.
Wait, can a median like come from the vertex to that?
Oh, and then there's that type of median. Thank you. Wow, I forgot about that one. So the median in a trapezoid is this segment. Yeah, why don't we just come up with new names for these things? So that's the median in a trapezoid. But you're right. Oh, wow, thank you. I temporarily forgot about that. A median in a triangle goes to a midpoint. It's a segment that goes to a midpoint. All right, so yeah, silly. We should just have different names for it. But next meeting, I'll make sure to bring it up. All the national math meeting.
Wait.
International meeting for mathematicians. Yes.
Wouldn't does a trapezoid have to be like that shape? Couldn't it be like a parallelogram except one?
Could be like that.
Yeah, but then can you like make the left leg a little more toward the middle? Like
that.
no, opposite
This?
that.
Well,
Oh
then
my
it's
God.
starting to become more of a parallelogram. Because these are parallel, but the more you make it like this, if these were parallel, then it would be, okay, why don't you show me?
I'm talking
How
about
is it parallel?
something like
Oh,
this.
what happened? How?
Like, at least one pair. I'm not saying that. I'm
No,
just
I
saying,
understand.
I'm
Is
not
this a
saying it is.
trapezoid?
That's just what they're saying. Well, if there's, as long as these aren't parallel, these are.
Okay.
Just one, exactly one set of parallel sides. So you just drew it, those are parallel, and you just drew it so these were not parallel. So yeah, as long as these are.
Based on that definition, would a square be a trapezoid? If it says that
It has it, yeah, because yeah. See, this is when it gets crazy. I know. Because a square is a type of
Is an
parallelogram.
octagon a trapezoid?
No. No.
What about a four-sided
That's
octagon?
why, let's just stick with exactly one pair of parallel sides. All right.
No.
Now,
Stop talking.
it's Madison. Now here's the properties. They are going to be very similar to the ones for triangles. So just as in a triangle, do you remember in a triangle the isosceles triangle theorem? If you have two congruent sides, then what happens? Isosceles triangle theorem.
Two angles on the bottom.
The opposite angles are congruent, yeah. It's isosceles triangle theorem. Same thing for trapezoid. This, right here. Both, I don't think this is called the isosceles trapezoid theorem, but it really should be. It just says if you have an isosceles, where's my isosceles trapezoid? I guess I'll draw a new one. Oh, here, it was this one. If you have an isosceles trapezoid, then the opposite angles, the base angles are congruent. Both pairs of base angles of an isosceles trapezoid are congruent. Now, you might say, well, both pairs. Well, that's one pair. These up here are also congruent. The reason is because this angle D and angle A are supplementary because parallel lines, they're same side interior. Same with C and B. C and B are supplementary. So if these were congruent, so would these. For example, it's an isosceles trapezoid, and we knew these were both 80 degrees. Well, 80 is supplementary at this one, so it has to be 100 because they're same side interior. And same thing here, same side interior, so this one would have to be 100. And so then these are also the base angles. So that's why it says both pairs. I'm just explaining why. Next up, the diagonals are congruent. Like a rectangle, the proof of this, which we'll do in a minute, is just like the rectangle one. The diagonals themselves are congruent. Now, it's only for an isosceles trapezoid. So if I do more of Charlie's trapezoid or a right trapezoid, those diagonals are certainly not the same length. Right? Definitely different. But as soon as the legs are congruent, then the diagonals will be the same. Okay, finally, do you remember for a triangle, when you had a mid-segment, the theorem was this. The side is parallel to this side, and this length is half. Like if this was 4, this would be 8.
Yeah.
That was the triangle mid-segment there. Basically the same. They should call it the trapezoid median theorem. I don't think there's really a name. It's basically the same. The median, this segment, is parallel to the bases. Similar as before. And it's half the sum. So whereas this one was simply half of 8. Well, I can't quite do that here because there's 2 bases. If this is 4 and this is 10, this will be half the sum. Sum is 14, so this would be 7. I'm trying to mirror how similar that these are with some of the triangle ones that we've done, and then this one with the rectangle one. Very similar. So, all right, let's do some examples. I want to do one proof. Any questions though right now about the properties for trapezoids? So just so you know, any trapezoid, this is the only new property about the median. But then if you get an isosceles trapezoid, there's 2 new properties. Okay, let's prove this first, not the first one, but the one about the diagonals being congruent. I'm going to stick with the 2-column proof for now. Just flow chart soon. That's an isosceles trapezoid. That's all that's given. We're going to show the 2 diagonals, AC and BD, are congruent. And surprise, surprise, we're going to show the triangles are congruent, like we've done all unit. Now, I want AC and BD. If I choose, so it's all about choosing the right triangles. If I choose the smaller triangles, top and bottom, left and right, I could, but then I'd have to do some segment addition. And actually, I don't even think you would get that on this one. I think we wouldn't have enough information, or it would take us a lot of steps. Instead, why don't we choose, like we did the rectangle. If you look back at the rectangle diagonal proof, it's almost the same. Why don't we choose these triangles? Because then if those triangles are congruent, AC and BD match up. As I normally do, I'm going to redraw it here. If you would rather, you don't have to. It's just overlapping triangles. If you'd like to redraw them, it can sometimes help. So I'll show it on this diagram, and I'll show it on the separate triangles. Okay, first thing I'm going to do is just a definition. We have an isotrap, an isosceles trapezoid. And if you look back at the definition, congruent legs. The legs are congruent. Just by definition. Those are the legs. Well, it didn't say which sides are parallel, but can we, I mean, A, B, and B, C are not going to be the parallel sides. They should be a little more clear that these would be the parallel ones. think we can all tell it's not going to be AD and BC parallel. They would intersect. All right, so AD is congruent to BC. Just the definition of an isosceles trapezoid. Just that they're congruent. So definition, the legs are congruent. Definition of isotrap. That's how I abbreviate mine. You can write it out if you want. Isosceles trapezoid. Oh, and on there, separate triangles. Anybody see another side up there? It's going to be congruent. Why? Shared side. Thank you. Why is that bottom shared side between the triangles? DC congruent to CD. Oh, and it is D to C in the red triangle, and then C to D in the blue. Reflexive property. What else? Now, we're not going to get the third side because that's what we're trying to prove. So we're going to have to get the triangles congruent, and then the third sides will be. So we need an angle. There's nothing else we know from trapezoids, just a trapezoid definition, nothing else from the diagram. So I'm going to bring back in a property we just learned. And I would, if this was an assessment question, I'd have to tell you, yes, you can use other theorems about trapezoids. It was the first one we just learned about. Base angles are congruent. It is an isosceles trapezoid, so the base angles are congruent. There's two sets of base angles. I will just choose the ones that are in my in my triangles. So I choose angle ADC congruent to angle BCD. And that property, again, you just have to write it down. It's not like corresponding angles theorem. You just got to write it out, this whole thing. Base angles of an isosceles trapezoid, I put isotrap, are congruent. So again, base angles of an isosceles trapezoid are congruent. All right, we finish it up pretty quick. Two sides and an included angle. Two sides, included angle. So the triangles are congruent by SAS. Triangle ADC congruent to triangle BCD by SAS. And therefore AC is congruent to BD by CPCTC. So yeah, if you look at the rectangle one we did, steps 5 and 6 are the same. Of course, 1 given. Step 3 is the same. We do a shared side. The side ones here are congruent in a rectangle because opposite sides are congruent. So this one's slightly different. And then in a rectangle, it's right angles as these angles. It is, so if you look back, I mean, if you put these side by side with the rectangle one, where is it at? To show right here why rectangle diagonals are congruent, it's almost the same. It's really, really the same. All right, well, any thoughts with that? I want to do a few little examples with traps. Proof though, not bad. Okay. Let's do some examples. We'll move on. I'm only going to talk for a couple minutes about heights. Let's look at this one below. I have median MN in an isosceles trapezoid. You know, actually, I don't think anything I'm going to do it needs to be an isotrap. It could just be, yeah, actually, this could just be a regular trapezoid that would work. So EF in part A, find MN, so find that segment. If EF is 12, DG is 14. I'm gonna do I'll show you the little property I'm gonna use, but any thoughts on MN without doing the work? 13. Basically what? Did you see like add +1 here and -1 here and you get there? Oh, what'd you do?
I add them together and divide by 2.
Yeah, this is what half of the sum is really what the property says. So you're right, it's really half of 26. Oh, sorry, half of 26, which is 13. It's an average. So you could actually just do this where you add and subtract. It's the same value, it would get you there. Part B, so it just gives you a different part of the diagram. It says find DG, so I want this one. EF is 20 and MN is 30. So I can show you the setup for the work here, but without doing the setup work, any thoughts on DG? 40. 10 this way, 10 again, it would be at 40. You can verify it, half of 20 and 40, that would be 60. And that works. Now, if you were looking for, you call this X. If you're looking for an equation, you're more like, hey, I like this equation to solve it. It would be the median 30 is half of 20 plus X. Probably a little easier just doing it this way, but some people like the equation version. Okay. I'm going to move on to the back side. I think we've done this, and you'll do it in the practice, and we'll sum up that one. Any thoughts on those? One more that's similar to it. What if all the lengths are in terms of variables? So find the lengths of these segments in the trapezoid. This is a midpoint because those are congruent, and so is this one. That, therefore, is the median. It's just the definition of median. Now, this one, since you could do a guess and check, maybe that would work. That might take a while. There is an equation form that's kind of the only surefire way to do this one. Okay, it says the median is half the sum. So X is the median. That will equal half, and then I have to do the sum of the other two sides. So I have to sum 2x and x. That would be 3x. And I'll sum -8 and -12 and get -20. So again, I just added these, 3x, added those, -20. I bet most of you want to distribute, and that will be fine. That'll get you the right answer. I want to show you how there's another way to do it, though. So if you distribute x, you'll get 1.5x and -10. And then you can subtract and divide. One other way I want to show you, though, that might be helpful, I think, especially Algebra 2 next year, you'll do this method more, is getting rid of this coefficient. So basically, in order to get rid of that, the opposite of half is 2, like multiplying by 2. Right now it's kind of divided by 2. So if I multiply both sides by 2, this is times 2, it'll cancel that out. The left side will now be 2x, and the right side you do not distribute in, you cancel the half. So it's just 3x minus 20. Might have done that in Algebra 1 last year solving. If not, you will definitely do that next year. So essentially the same number of steps. So it's really up to you how you'd like to solve it. You finish solving, I subtract x and add 20, and you get 20. You would get 20 here as well. So if I want to find the lengths, this is 20, this is 20 minus 8, which is 12. And then we could actually find this one, plus 8, plus 8, plus 8. Or if you plugged it in, it'd be 2 times 20 is 40 minus 12, which is 28. Well, anything else about trapezoids? comments? Let's talk about kites to finish up. I'm going to tell you what they are, 2 properties, and 2 quick examples. I'm not going to do example B below. I'm going to do A and C. So we talked about how they have no parallel sides. Okay? Now that's actually not the definition. It's just kind of assumed. Like, I mean, if, right, even if you looked at a standard trapezoid, like, yeah, there's no parallel sides up there. So it's not the definition. It's just something we know is true. There's no parallel sides. So if you'd like, you can make a note that there's like 0 parallel sides. The actual definition, though, is 2 sets of adjacent congruent sides. In the diagram here, it's JK to JM. Those are congruent, like traditional kite, top 2 sides. And then KL and ML. So that's the definition. It's not a trapezoid, it's not a parallelogram, it has none of those properties. I'm going to focus on 2 theorems. I'm not going to do these 2. First 2, these are the most important ones. So you know how a parallelogram has 2 sets of opposite angles congruent? This one has 1 set. The kite has 1 pair of congruent opposite angles. In a traditional looking kite like this, it's the side angles. In the diagrams here, it was JKL and JML. The other thing is the diagonals are perpendicular, just like a rhombus and just like a square is like a rhombus. That one's important because, again, it makes right triangles, and you can do things from there. One other comment, remember how a rhombus made 4 congruent triangles? A kite's diagonals make 2 congruent triangles, these 2, and then these 2 are also congruent. It makes 2 pairs of congruent triangles. Yeah.
So, angle K and angle M are congruent. Does that mean angle J and angle L are supplementary?
First of all, in this diagram, you have to say JKL, but I know what you mean as K. Second, no, because here I was trying to think through it. Well, here's an example, I guess a counterexample, because we're going to do an example where that's 101, that's 48. They're not supplementary.
So does that just not even make sense, or is that like, do you understand where I'm getting that from? Where they would add up to?
Maybe you're thinking if it's a right kite, if they're 90, maybe that's what you're thinking. Because in a quadrilateral, the sum of the angles is 360. And so maybe that's what you're thinking. Then these would be like this and this would be supplementary if these 2. Maybe that's the property. If these 2 are supplementary, then these 2 will be. That's pretty much as far as we can get.
Is that a thing like a right?
Yeah, right kite just has a right angle. We're not going to do much with right kites. But yeah, if you have, but if this is a right angle, you have 2 sets of right angles. What if you, yeah, but it could be just one of the other angles is right. We're just focused on general, just a kite and its properties. Good questions, guys. Thank you. Any others before? Yeah. How about hold on 1 second. Let me just finish these up. So find the missing angle measures. We're going to do A and C. So this one finds missing angle measures. I mentioned how the sum of the angles is 360 in a kite. Sorry, in a quadrilateral. 360, I subtract off the 101, I subtract off the 48 to find out how much is left. That'll be 149, so I'll be left with 211. The property for kites, this pair of opposite angles is congruent. And so to find angles 1 and 2, I can just divide by 2. 105.5. Oh, that's Christmas colors.
Please stop.
I got to take off my tie. And then just hold it back there or something and just look at it. It's good.
Green.
Gray. I'm looking at it. So, oh my gosh, you guys need to get your eyes checked. Let's move on to C. We have a kite to finish up, find the perimeter. This kite has congruent adjacent sides. I don't know if there's both 12. These are congruent, so they're both 20. I will add these to get 40, add these to get 24. Okay, so we get 64. So quick examples. A lot of these examples you'll find with traps and kites, they're mostly just quick, finding little angles, little sides.